Okay, welcome back to the afternoon session. First talk contributed by Anna Peón, and the title is Equivariant, Multiplicities, and Reducible.
Thanks, Steve. Thank you all. It's a great honor to be here today to celebrate 50 years of Nigel's mathematics. The starting point of this talk is this paper, which was published in 2022, although the results date back to 2021, still very recent. This is, again, one example of great mathematics produced by Nigel, very, very recent. Thanks so much, Nigel, for this new contribution that keep inspiring me after many others, as you already know. So the keywords here are very stable Higgs bundles. So actually, it's a new contribution, but I should say it's stacked onto others because we have Higgs bundles here, which is, dates back to 40 years ago, and all these ramifications to, for example, mirror symmetry. But the new ingredient of this paper is this notion of variability of Higgs bundles. So variability, I'm sorry for using this word, Oscar, I see you, has been around for about 40 years too, and dates back to Lamont. But in this context of Higgs bundle, it appeared for the first time in this paper of Nigel and Tamas. Okay, so I'll get back to that in a minute. But an ingredient that's going to be important as well as my talk is the application to a relatively simple and basic question about the moduli space of Higgs bundle, which is the multiplicity of some components of the global nilpotent cone. Okay, so I was going to give a talk, but it's wobbly and not very neat, so I'll just do an iPad talk instead. So let me start by the beginning, so with some preliminaries and motivation. And I apologize to Marco because there's just one more to go on Higgs bundles. Right, so I'm going to work on the moduli space of Higgs bundles that I'll denote by M, capital M. So this is the moduli space of Higgs bundles of fixed rank and degree, of rank n and degree d, on a Riemann surface X of genus at least 2. So 0 certainly, but 2. Okay, so this is a scheme that has a very rich geometry, and one of these features that we've encountered in the past few days is the so-called Hitchin map, which is mapped to a vector space of R and affine space. So in this case, I will be working in the context of vector bundles. So the Hitchin base, so the target of this Hitchin map, is the direct sum of the sums of all differentials of degrees 1 to n. This is the Hitchin map. And it assigns to a Higgs bundle E phi the characteristic polynomial of the Higgs field. So I'm going to recall that E is a vector bundle of the given rank and degree that's semi-stable. And phi is the Higgs field, which is a twisted endomorphism. So a section of the endomorphism bundle by the canonical bundle of the Riemann surface of the complex curve. So this naturally contains cotangent space, the tangent space of the modular space of bundles, and these would be the space of all the differentials on a given bundle, in the case when E is stable. Okay, right, so this Hitchin map has many great features. So the generic fibers are smooth, are abelian variety. So it would take a generic point. The generic. All right. But probably the most interesting fiber is the nilpotent cone. So the fiber over 0, which is the nilpotent. You need to disconnect.
It's connecting right now. It'll pop up.
I'm going to move from.
I'll connect it back.
Right. So this fiber is the most singular of all. It's so while the generic fiber is an abelian variety, is connected, is smooth. The nilpotent cone is reducible, so it has different irreducible components, which are not even no, they are not reduced. Okay, so something that's interesting as well from the nilpotent cone is that it contains a deformation retract of the moduli space that can be realized via the C-star action that we've already encountered. So C-star acts on the moduli space of Higgs bundles just by multiplication. So one takes a parameter T, C-star, and it acts on a given Higgs bundle just by multiplication of the Higgs field. Right, so by taking limits to 0, so letting this Higgs bundle flow, one hits a point. So first of all, existence of limits are, so the limit exists, for example, with properness of the Hitchin map. And the Hitchin map is also equivariant with respect to the C-star action. So the action on the base is going to have certain weight, but still it's since it's given by homogeneous polynomials, the limit at 0 is going to hit the nilpotent cone. Not only that, but it's in particular a fixed point of the C-star action. Okay, so, all right, let me define as a piece of notation. So given a fixed point of the C-star action, I'll denote by E plus the downward flow to it or upward flow from it. There are different tastes for this. I'll talk about downward flow to the point, which are Higgs bundles such that the limit at t goes to 0. This C-star action equals. Okay, right, so here, so one starts from a given Higgs bundle, say E0, and sorry, A5, that lies over the generic point of the Hitchin base. So by flowing t to 0, one will hit the nilpotent cone. And there are different fixed point components. So one of them is just the moduli space of bundles. So this defines a full component of the nilpotent cone, which is Lagrangian and of pure dimension. But there are other components. They won't describe full components of the nilpotent cone, but they actually determine them. So when the underlying bundle is stable by flowing into the nilpotent cone when Higgs is moduli space, but I could have started with Higgs bundle whose underlying bundle is not stable. So an example of this is showing Brian's piece of talk is the Hitchin section, which is a direct sum of line bundles. So in rank 2 we have form. So the underlying bundle is unstable in spite of the Higgs bundle being stable. Right, so when one flows this to the nilpotent cone, it will hit a higher, say, component of the fixed point lattice. And in fact, one can perform the same kind of a procedure, but instead of taking an arbitrary Higgs bundle, one can take a point of the nilpotent cone, and since the Hitchin map is proper, these fibers are also proper, so one can in fact take the limit at infinity. And this procedure is by considering irreducible components of the fixed point lattice and taking these limits at infinity, so considering all Higgs bundles in the nilpotent cone that flow at infinity to these fixed point components, one can recover all irreducible components of the nilpotent cone. Right, so these fixed points contain an enormous amount of information about the nilpotent cone and therefore about the moduli space of Higgs bundles. Okay, now these
You're gonna have to share it again.
again.
Yeah.
Okay, yeah,
Mhm.
that's it. Good. So fixed points components were, I mean, the fixed point set was studied firstly by Hausel and Simpson. So I've already mentioned an example. So there's when then the nilpotent, and the order of nilpotency is 1, that means that the Higgs field is 0. The fixed point component is the moduli space of bundles, which sits into the Higgs bundle moduli space. There's some morphism. It's an embedding on the smooth points, which sends our given bundle to the bundle with the 0 Higgs field. So it's in particular inside the nilpotent cone. And this is the realization of the corresponding fixed point set. But there are many others. So when the order is at least 2, then the underlying bundle has the form, it's a direct sum of, say, order S, which is at least 2 of S bundles, and the Higgs field maps the different bundles to one another. So, I mean, there's a filtration given by the different terms, and the Higgs bundle respects this filtration. It's important with respect to it. Okay. Now, there's been a lot of work on these subspaces of the moduli space. And there are invariants that one can assign to each, which is called a type. So the type of the fixed point is given by the ranks of all the terms. And there are degrees. We'll often refer to the type only by the rank, but often when it's to specify. Also, I mean, when it's to specify also the degrees. And it's been proven, so I'll cite here, there's Bradlow, Garcia Prada, Gaussman, and Heinloth on the one hand, but it's built on much former work. And also Bozek in the non-smooth case. These people prove that, in fact, these invariants determine the irreducible component of the fixed point set. Okay. All right, so with respect to the C-star action, there are 2 natural types of fixed points within the nilpotent cone. So if one starts in the nilpotent cone, one can it certainly float to 0. And in that case, one is going to hit a point in the intersection of 2 irreducible components. But not all points are going to be attained like that. So the following definition, which started with Drinfeld, probably, he's cited by Lomon in his paper about the nilpotent cone and was generalized by Hausel and Hitchin. A given fixed point is very stable if the downward flow to it intersects the nilpotent cone exactly this. So, for example, if one considers the fixed point that's given by a stable point on the zero Higgs field, then what's E plus? Well, in this case, E plus is just the space of all Higgs fields on the given bundle, right? So the fixed point is very stable in this sense, if and only if E is very stable according to Grunfeld's definition. Namely, it doesn't admit a non-zero nilpotent Higgs field. So for according to Dürmfeld's definition, all strictly semi-stable points are wobbly, namely they're not very stable. According to this definition, in these terms, that's not true anymore. There can be very stable, strictly semi-stable bundles and wobbly, strictly semi-stable bundles. So I've used the word without defining it, but a point that's not very stable is called wobbly. Okay, so we have one word from the title. All right. Now, something that Hausel and Hitchin proved in this paper that I showed at the beginning is that if one has a very stable point, there's a lot of information there's a piece of information at least that one can deduce about the component of the nilpotent cone that contains it. Namely, one can compute the multiplicity. So if given a fixed point that's very stable, then the following map, so one can restrict the Hitchin map to the downward flow to this point, and it turns out that this is proper, and in fact this characterizes variability. And in fact, and then therefore it has to be finite since it's a proper map between two affine varieties of the same dimension. And thus the degree is well defined. So, and the degree gives you the component very stable, and I should say smooth point. So stable as well. Then the degree of this map is the multiplicity of the irreducible component. Of the nilpotent cone contained in this point. Okay. Okay, so if one has a very stable point in an irreducible component, then one can perform this calculation. So for example, components that contain very stable points so the moduli space of bundles, and this was proven by Lomon. He proved that the very stable points are dense and open. The Hitchin component, for obvious reasons, because nothing can flow down to it as it's the top component of the moduli space. And this is a component of type 1, blah, 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 1, so n times. And in fact, another theorem proven in this paper by Nigel and Tamás is that any point of this type namely of type 111, is, sorry, not any point, any component of type 111 has very stable points. And these form a dense open set theory as well. Okay, so I'm going to define, I'm not, they did actually. So a component is called very stable if it contains a very stable point. Component of the nilpotent cone, I should say, or fixed point set. Let's say the fixed point set. And component means irreducible component. And other words, I'll call it Wobbly. Okay. Okay. So all right. So this notion is useful. In fact, well, their motivation was more on the side of mirror symmetry, but there are very basic questions related to the moduli space that can be answered when one has a very stable point. So the question is now, what happens with other partitions? Okay. Namely, this corresponds to the partition N, so type N, fixed points, and this corresponds to the partition, the finest partition. What about intermediate ones, right? The tip of the cone and the bottom of the cone are very stable, but how about the others? So the rest of the talk, I'm going to focus on fixed points of type N0 and 1. Namely, the nilpotent order is going to be 2, and I'll assume that N0 is greater than or equal to N1, and duality allows to pass from this case to the other one. So we only need to worry about this one. So let me start with an example that also appears in the paper that I cited at the beginning. Let's take in rank 3 partitions of type 2, 1, right? So I have a fixed point of the form F0 plus F1. So this is a rank 2 bundle. This will be a rank 1 bundle, and the Higgs field maps the line bundle into the rank 2 bundle. So Gaussen proved that the non-empty components of the nilpotent cone are classified by an invariant, which is the degree of the following. So F1 dual F0 K, right? So this is the Higgs field in the fixed point is precisely a section of this bundle. So this is a non-emptiness of say, or existence of semi-stable objects is bounded by so the invariant needs to vary between 4g minus 4 and g minus 1. And in fact, if generically one can see that the Higgs field has to be, I mean, the Higgs field is going to be saturated inside F0. So the image of, so F0, in other words, is an extension of F1K dual by certain quotient. And in fact, I don't need that, but anyways. So what happens is that when delta is strictly smaller than 3g minus 3, a Riemann-Roch computation tells you that there's always a section from this quotient, so into F1K. So taking, say, a beta here, a given section, one can cook up a Higgs field. Delta, yeah, sorry, I didn't. Delta is this invariant, yeah. Sorry. Right, so by Riemann-Roch, when delta is small enough, there are sections here. So one can cook up a nilpotent Higgs field. Right, so what I'm saying is that the image of phi is containing the kernel of beta. So when one composes, this is 0. And so one has the following. One can show that, say, the same underlying bundle with this Higgs field flows to the fixed point that I started with. So recall this is the fixed point as t goes to 0. And this turns this means that this is Wobbly. So for the components in the range g minus 1 to 3g minus 1, all the bundles, in fact, are Wobbly. I don't need this genericity condition, but in any case, various stabilities that are empty or dense. So it's enough to look at the generic ring. So the components with invariant delta at most 3 to g minus 3 are Wobbly. So this is conjecture. There's a conjecture in the paper by Hausel and Hitchin saying that, say, E contain in H minus 1, say, an irreducible component of the nilpotent cone. Is Wobbly if and only if delta varies in this range. All right, so how did I get to this conclusion? Are there any questions so far? They conjecture this for rank 3 only, yeah. That's right. Okay, so in the paper, they define some invariants. So okay, let's start with a C-star module. And then there is the composition, say, it's finite dimensional, so there's certain weight spaces that are denoted by V lambda. So the character for this C-star action of V is defined to be the dimension of each space times T minus. So they define for a given fixed point, 0 fixed point, one can consider the tangent space on, so this comes up with a C-star action, and in particular, there's a positive weight space. So the subspace where the C-star action acts with positive weights. So this is a C-star module, and the virtual equivariant multiplicity of this point, it's a function of t, and it's defined to be the character of, let me put in the right, of the symmetric algebra associated to this, the dual of this positive tangent space divided by the character of the symmetric algebra of the dual of the Hitchin base. And one can check that this is this has the following form: 1 minus t to the g, 1 minus t squared, 3g minus 3, etc. 1 minus tn, minus 1, and then the product over all weights appearing in the weight decomposition of the tangent, the positive tangent space of 1t minus, t to the given weight times the dimension of t plus, let me call this t plus 4 lambda. All right. Right, so they proved that if E is a very stable fixed point, then this virtual, so I should write it, this is the virtual equivariant multiplicity. So when a point is very stable, the virtual equivariant multiplicity is a polynomial with integer coefficients. And in fact, it does not depend on the particular generic point, but only on the component it belongs to. Right, so in particular, non-polynomiality of these invariants gives means that the generic point cannot be stable. Therefore, the component must be Wobbly. Right. So together with Christian Pauli from Nice, so we prove that the conjecture is true. And the proof, in fact, uses criteria for wobbliness. So so the situation is a bit more complicated in the case of points corresponds to the finest partition, but there are some similarities. So for example, okay, so a point is wobbly of type 2-1. There are three possibilities. There's if and only if, first of all, one could have that F0 itself is wobbly. So if there's a nilpotent, meaning that there's a nilpotent Higgs field on F0, in which case one can construct easily a nilpotent Higgs field on the same bundle that flows down to the fixed point. Another option is for F0 quotiented by F1k to have torsion. And this is the case that was observed by Nigel and Tamash in the case of, in the case of rank 1, it's not enough to have torsion, but it has to be double. But here there's enough room for the torsion to allow to construct. Anyways, torsion. This generalizes their criterion. And the second case is when H0 of S, or say F0, quotiented by the image of the Higgs field, A, dual, F1k, is non-zero. All right, so this classifies all possible wobbly points, but then one can observe easily that these are non-generic. These define positive codimension subsets inside the space of fixed points. And this is the only case where it can cover the whole component. But it's generic if and only if delta has the right value, namely it's smaller than 3g minus 3. So this proves the conjecture. Right, so the moral of the story is, in this particular case, polynomiality of the virtual equivariant multiplicity gives variability of the component. But one doesn't need to go too far to check that this is not always the case. So the next example is very similar. I'm moving to rank 4, type 3-1. So F0 has rank 3, F1 has rank 1, and again, one has a map from the line bundle to the higher rank bundle. Now, in this case, the same invariant, namely the degree of F1 dual tensor with K F0, this classifies the irreducible components in the range 6g minus 1 and 2g minus 1. And again, Riemann row gives wobbliness of all the components by the same argument. So the image of so there's the quotient F0. This always has sections for any delta. So they are all wobbly. but the virtual equivariant multiplicity is always polynomial. Okay. Good. So this is very different to the rank 3 case. And for the remaining of the talk, I'm going to explain what happens in general. So there are two examples. So there are two examples to keep in mind. The first one is the one I've just gone through, but which generalizes, right? So we are going to consider generically there's always an embedding from f1k dual to f0. So f0 can be expressed as an extension. This may be torsion when I say I'm going to take f0 and f1 of type n0 and 1. So if n0 equals n1, then s is it's maybe 0, but possibly torsion. There are many cases where it's non-zero. But assuming that it's non-torsion, then the invariant that we've been, so the degree of f1 dual f0k is again gives all the possible irreducible components, which are contain semi-stable points whenever this delta varies between 2 and 0 and 1 g minus 1 and n1 and 0 minus n1 g minus 1. Where equality here depends on whether n1 equals n0 or not. But in any case, for delta at most 3 and 1 and 0 minus n1, one can again construct non-zero sections of this model. Okay, so these components are going to be a wobbly. So let me remark here that for this to be true, I have to assume that n0 is different too. And well, for this to be true, the only problem is that for n1 equal to n0, these values give non-semi-stable components. So we're out of the range of interest. But there's a second example, precisely covering this gap. So let's consider the following point. I have a rank n0 bundle together with itself. Let me change the order to keep a coherent notation. So two rank n0 bundles, which are the same, except that one is obtained from the other one by tensoring by the dual of the canonical bundle. So that the identity Higgs field gives is the only option. So if we can find, now suppose we can find a nilpotent bundle, a nilpotent, okay, what does this mean? A section from k dual to fk, such that, so which seen as a section equivalently as a section of the endomorphism of A tensored by the square of the canonical bundle, which is nilpotent in this second sense, right? But then say of order k, then the Higgs field, which is given by the identity, and then beta is nilpotent of order 2k. All right. So So then this kind of fixed points, this fixed point like that is going to be wobbly. But in fact, this is always possible. And this is due to a theorem by Rousseau-Teixeira on Brill-Netter theory. That says that every bundle can be expressed as an extension of a certain form, say M of n, where the difference of say of degree dm and degree dn, and there's the Segre invariant that's expressed in terms of the degrees and ranks of these sub and co-bundles satisfy that there always exists a map from n to mk. So this is a consequence of their theorem, but it's pretty straightforward, right? So such a map, such a section, in fact, gives an nilpotent Higgs field, k-squared, sorry. K-squared. So such a map always gives a k-squared twisted nilpotent Higgs bundle on F, right? Because I just project to n, map to m k-squared, and embed again in f k-squared, and this has given me the nilpotent Higgs bundle that I needed. Okay. Okay, so this is always possible. And as a corollary, so I should mention maybe for those people that are interested that this particular case, so this particular case corresponds to delta equals 0, which is the maximal Toledo, obviously. So the minimality of delta goes opposite with the minimality of the Toledo. So maximal delta is minimal Toledo and vice versa. Okay, all right. So we have these two key examples, and how about more general points? Well, the remark is that generically, if one has a Higgs bundle of this form, one can consider a sub-Higgs bundle, which is F0. Inside F0, there's F1K dual, generically always, and this is a Higgs bundle of the form that I just expressed. So if one can extend this beta I just talked about to something in 0, that's from F0 to F1K, then we're done proving wobbliness. Great, and so the theorem is that for partitions different to 1, 1, which is covered by Hausel and Hitchin's paper, and 2, 1, so not in here, then all components are wobbly. And they fall into, there are more wobbliness possibilities, but what realizes wobbliness generically are one of these two possibilities. First, if the invariant delta is at most 3 and 1 and 0, 2 minus 1, then it admits order 2. So it flows, the fixed point flows up to So the downward flow, say, to the nilpotent cone, its closure, to the fixed point intersects a component of type of order 2. So so n0 prime and 1 prime. It's not going to be the same ranks, but it's of order 2. And if delta is greater than that, then this falls into the category of these other examples. Then the downward flow to it closed intersects a component for a different partition. And now I don't remember exactly what, but it had 4 credit pieces. So the order is 4, so 0 prime and 5. Okay. All right. Any questions? Okay, so there's a remark, and it's the following. So this was observed already by Simpson. Any fixed point is a Higgs bundle for a real form, and in this case, they are UPQ Higgs bundles. So let me remind you what these are. They decompose as a direct sum of 2 vector bundles of rank P and rank Q.
Sorry,
Yes.
just to make sure I wrote it down correctly. A little bit. The first case, this means if I go along this nilpotent direction for my fixed point, I'll hit something in the form n0 prime n1.
That's right. Yeah, that's right. So I'm closing.
And the second case, can one of those n be 0, or does it have to?
No, it's always generically it's always non-zero, so it's order 4, nilpotent order 4. Okay. Great. So all fixed points are UPQ Higgs bundles. Why is that? Well, if one takes so fixed points are of this form. So one can add all the even bundles on the one hand, and then all the odd ones. Maybe I need a -1, but anyway, and then one obtains a Higgs field of this form that exchanges both subbundles. Right. Okay, so now if one has a bundle, so just one more remark is that the U and the P and the Q vary depending on the ranks of the bundles, right? So in the case of order 2 fixed points, then they are, so order 2 are UN0 and 1 Higgs bundles, right? So one can in fact try to check. So this variability notion makes sense also within the smaller moduli space of Higgs bundles that restrict their structure group to a real form. So if one has a UN0 and 1 Higgs bundle, one can decide whether it's very stable, UN1 and 0 and 1 very stable, meaning there's no nilpotent Higgs bundle there's nothing in the modular space of UN0 and 1 Higgs bundle flowing down from the nilpotent cone to this point. Or conversely, it would be wobbly. So if there is something flowing down to it inside the modular space of UN0 and 1 Higgs bundles, right? So it needs to be fixed, otherwise it doesn't make sense what I just said. So what I'm saying is that the downward flow to it intersects the moduli space of U and 0 in 1 Higgs bundles at the nilpotent cone outside the given fixed point. So this is a remark from the constructions that I just explained. So a priori being, one has given a component of U and 0 and 1 fixed points. There are wobbly points. And there's a priori and a smaller subset, which are U and 0 and 1 wobbly points, right? So an example, if there's torsion in the quotient, plus some conditions, I mean, it's torsion plus conditions, then there is a downward flow, but it's realized by a non-trivial extension of F1 by F0 by N1. So it's not in the right moduli space. Right, so the corollary or the...
It should be either not empty, but this should be the definition of very stable.
Say that again, sorry.
Shouldn't it be not very stable?
Non-empty, yeah,
Okay.
thanks, sorry. You're right, yeah. Right, so the corollary or the remark is that generic points in order to fixed point components for rank at least 4 are wobbly if and only if they're U and 0 and 1 wobbly. But it's not true for all the points, just for the generic points. So I should remark here, there's a related notion that was defined by González Hausel, and they consider even variability. So so instead of considering downward flows intersecting a fixed moduli space for a fixed UPQ, they allow for any UPQ to appear. And in fact, they work out, so González Hausel, they classify even very stable points of type 1111. And in this case, for this partition, even variability and UNN or UNN plus 1, depending on the parity of the rank, match. So in this case, the notion is the same, but it's slightly different in general. Okay, I don't have much time left, so I'll just explain. I'll just tell you about it. So there were 2 things that I started with. First, variability and its uses, right? And secondly, sorry again for the variability word. And secondly, these invariants that seem to detect very stable points sometimes and not others. So what happens with the virtual equivariant multiplicities in general? Well, in fact, I can give you an expression of the virtual equivariant multiplicity for arbitrary points of order 2. And it turns out that it's sometimes, for some invariants, it's always a polynomial, so it doesn't detect wobbliness at all. And this is the case, for example, for partitions of type n minus 1, 1. It's always polynomial. For other partitions like n halves, or n half, n minus 1 half, n plus 1 half, right? It's not always a polynomial, but it doesn't detect all the cases. So for some invariants, it's a polynomial, and for some it's not. And I haven't managed to detect an interesting pattern. I'm still studying this. Okay. Right. So, I mean, this is an option, but there are other invariants that they define, and these are related with mirror symmetry. So let me briefly tell you what happens in that case. Sorry. Right. So for very stable points, one can, I mean, this holds for any point. So the downward flow together with the structure shift is a BA brane. It's a Lagrangian with a bundle admitting a flat connection. And when the point is very stable, it's possible to compute the dual BBB brane. So this is realized by some hyperholomorphic shift that's supported, since this is a multi-section, it's supported on the whole moduli space. And it comes also with the equivariant structure. Right, so there are some equivariant Euler characteristics that one can compute in some cases. So this is the virtual Euler pairing of, say, two, I mean, it's not quite the right way to say it, but say two very stable points is given by the equivariant Euler characteristic of a given restriction of the hyperholomorphic shape. So the important thing is that this, for mirror symmetry, one can argue that these have to be polynomials when points are very stable. And there's an expression that gives that relates, say, the Euler pairing of E and E tilde with the Euler pairing of E tilde and E in these terms. So why is this useful? Well, in fact, the hyperholomorphic shape has been computed in this type 111 case only. And in order to perform computations, one needs a explicit form. So imagine that one has another fixed point and take E to be very stable of type 111, then this expression allows you, so it gives again an abstraction for very stability of the non-very stable point, right? So if one can prove that this pairing is not polynomial, then one needs to have wobbliness. Okay, so I mean, I have some examples here, but unfortunately, this is not a complete, this doesn't classify wobbly components either, at least not totally. And this is all I had to say today. Thank you.